Deep in the cosmos spins a star so dense a single teaspoon of it would weigh billions of tons. It's called PSR J052c0607, the heaviest neutron star ever detected. How can something so small be so impossibly massive? Tonight we'll uncover its secrets. If you enjoy this journey, please like, subscribe and share, and tell us in the comments, what would you ask if you could stand near a star this extreme? Thank you for watching. Now, let's begin. The Milky Way stretches as a broad, pale band across the sky, a disk of stars, gas and dust that circles calmly around its center over spans of hundreds of millions of years. And in this wide galactic structure, the stage is set for the existence of this neutron star. Spiral arms wind around the central bulge tracing lanes of star formation, and clusters of young blue stars, while older redder stars fill the thicker disk and the more diffuse halo that surrounds the galaxy. Between these stars lies a thin mixture of gas and fine dust grains, cool in some regions, warmer in others, shaped by shock waves from supernova explosions and by the steady radiation of ordinary stars. The overall mass of the galaxy, including its unseen dark matter halo, binds these components together through gravity, guiding the motion of stars in orbits that are not simple circles, but long, slow paths influenced by the combined pull of all the matter in the system. Among these many stars, a small population follows orbits that take them well away from the main disk, out into regions where the stellar density is lower, and the night sky when seen from within would appear thinner and more sparsely filled. This neutron star resides in such a region, orbiting in the outer parts of the Milky Way, far from the busy central zones, yet still deeply bound to the galaxy as a whole. From the point of view of an observer on Earth, the location of this neutron star is defined not by physical landmarks, but by angles on the sky, measured relative to the plane of the galactic disk, and the familiar constellations that form patterns only from one vantage point. The line of sight toward it passes through layers of interstellar gas and dust, which absorb and scatter some forms of light more than others, changing the way the galaxy appears in different observing bands. Radio waves penetrate this material more easily than visible light, while high-energy gamma rays and X-rays also carry information from energetic processes near compact objects, so astronomers map the Milky Way in many wavelengths to gain a full picture of its structure and of the phenomena within it. Surveys of the galactic plane in radio-infrared, X-ray and gamma-ray bands reveal not only bright star-forming regions and remnants of past supernova explosions, but also point-like sources that do not match ordinary stars or nebulae. These compact sources often trace the presence of extreme objects such as neutron stars and black holes, whose strong gravity and magnetic fields focus energy into narrow beams or powerful outflows. The Milky Way contains many billions of stars, yet only a small fraction end their lives in supernova explosions that leave behind neutron stars, and only a subset of those neutron stars become pulsars rotating rapidly and emitting beams of radio or high-energy radiation that sweep through space. These pulsars are scattered through the disk and halo, some near their birthplaces in the spiral arms, others kicked into high-velocity trajectories by asymmetries in the explosions that created them. Over time, their orbits carry them around the galactic center so that a pulsar observed today may no longer lie near the remnants of the star-forming cloud from which its progenitor star was born. This neutron star is one of these rare remnants, but it sits in a context shaped by the overall structure and history of the Milky Way. The thickness of the stellar disk, the distribution of gas and dust, and the pattern of spiral arms all influence where massive stars form and where they eventually explode. Regions nearer the galactic center tend to have higher densities of gas and stars, leading to more frequent massive star formation, and therefore to more neutron stars, while in the outer disk and halo such events are less common, and compact remnants are correspondingly more widely spaced. The path of this pulsar through the galaxy can be traced in models that combine its measured motion on the sky, its estimated distance, and the gravitational potential of the Milky Way yielding an orbit that may be inclined with respect to the disk and elongated rather than circular. Such an orbit would carry it above and below the plane over tens or hundreds of millions of years through regions of different density and radiation background, but always under the same large-scale gravitational field that governs the movement of stars' gas and dark matter together. From Earth, the background of the sky in the direction of this neutron star includes the diffuse glow of unresolved stars in the disk and the faint emission of interstellar gas, but careful observations in radio and high-energy bands allow astronomers to separate the point-like emission of the pulsar from the broader galactic background. Mapping these sources across the sky gradually builds up a view of the Milky Way, in which each pulsar becomes both a beacon and a probe tracing the distribution of matter and magnetic fields along the line of sight. In this way, the galaxy is not only a setting, but also a medium through which signals propagate slowed, scattered and delayed by the ionized gas that fills the space between stars. For this pulsar, the time delays of its signals, the amount of scattering, and the brightness in different bands all carry information about the intervening material, as well as about the source itself. The combined pattern of such measurements for many pulsars across the sky helps to refine models of the structure of the galactic disk and halo, the thickness of ionized layers, and the presence of large-scale features such as spiral arm segments and bubbles carved by past episodes of star formation. In this broader picture, this neutron star contributes only a tiny fraction of the total mass and light of the Milky Way, yet it has an outsized role as an indicator of conditions both at its own location and along the path between there and Earth. The Milky Way is not static. Its spiral pattern winds slowly, its gas flows inward and outward, in response to gravity feedback and interactions, and its stars orbit in a collective, but not perfectly ordered motion. Within this dynamic setting, this neutron star continues its path, a compact, dense remnant, moving quietly among the far larger number of ordinary stars that share the same gravitational home, its extreme properties set against the calm average structure of the galaxy that contains it. The sky in high-energy light looks very different from the familiar view seen with human eyes, and surveys in gamma rays and X-rays reveal a pattern of bright patches and diffuse glow that traces some of the most energetic processes in the Milky Way. Instead of steady points of starlight, these maps show sources associated with supernova remnants, pulsar wind nebulae, compact binaries, and distant galaxies whose active nuclei shine across cosmological distances. A space telescope designed to detect gamma rays sweeps the sky again and again, building up a catalogue in which each source appears as an excess of high-energy photons above the surrounding background. Among these sources lie objects that do not match any known counterparts at lower energies, catalogued simply as unidentified gamma-ray emitters. Many of these turn out after further study to be pulsars whose rapid rotation and strong magnetic fields produce beams of radiation that include gamma rays as well as radio waves. This pulsar belongs to that population, and its path into the scientific record begins with its appearance in such a high-energy catalogue as a source with no obvious association in visible light. When astronomers examine the gamma-ray data collected from the direction of this neutron star, they look for the telltale signs of pulsation, a regular pattern in the arrival times of photons that would indicate a rotating lighthouse-like beam. The analysis involves folding the arrival times over a wide range of possible spin periods and their slow changes, searching for a combination that brings the photons into phase and reveals a peak in the light curve. For many sources, this coherent signal is difficult to extract directly from gamma-ray data alone, especially when this neutron star spins hundreds of times each second, because the parameter space to be searched is broad and the number of photons is relatively small. In such cases, multi-wavelength observations become crucial, and astronomers turn to radio telescopes and optical instruments to search for candidate counterparts within the error region of the gamma-ray source. In the case of this neutron star, deep optical imaging reveals a faint star-like object whose brightness varies periodically over a timescale of a few hours, a hint that a compact binary system may be present. Careful monitoring over many nights shows that the light from this star changes in a way consistent with heating of one side of a very low mass companion by a nearby energetic compact object. On the side that faces this pulsar, the companion appears hotter and brighter, while the far side remains cooler and dimmer, so that as the orbit carries the companion around, the observed brightness rises and falls in a repeating pattern. Spectroscopic observations which spread the light into its component wavelengths allow measurements of the companion's motion toward and away from Earth, tracing its orbit through shifts in the positions of absorption lines. From these data, astronomers infer the orbital period and the amplitude of the companion's velocity, building a picture in which a massive but compact primary object exerts a strong gravitational pull on a very light secondary star. With this optical information in hand, radio astronomers target the position of the source, with sensitive receivers tuned to frequencies known to reveal pulsar emission. By recording the radio signal over long integrations and processing it, to remove the dispersion caused by free electrons in the interstellar medium, they search for periodicities that would indicate a spinning neutron star. When a clear set of pulses appears repeating hundreds of times each second with remarkable regularity, the link between the gamma-ray source, the optical binary, and this pulsar is confirmed. The precise timing of the radio pulses tracked over many orbits of the binary allows astronomers to refine the parameters of the system and to determine how quickly the pulsar is spinning down. That is how its rotation gradually slows as it loses energy through radiation and particle winds. For this neutron star, the measured period lies in the millisecond range, meaning that it turns several hundred times each second, placing it firmly in the class of millisecond pulsars that have been spun up through past episodes of mass transfer from a companion. The high-energy data complement this timing picture by showing that the gamma-ray emission is modulated at the same spin period, confirming that the beams from this pulsar carry significant power at the highest photon energies detectable by current instruments. Meanwhile, the optical data continue to refine the properties of the companion, indicating that it has a mass far below that of the Sun, and may be in the process of losing material under the combined effects of gravitational pull and intense irradiation. Although the detailed modelling of the companion and the exact mass of this neutron star involve additional steps, the discovery path already shows that the object is both very dense and very fast spinning. The coordinated use of gamma-ray catalogues, optical imaging and spectroscopy, and targeted radio timing illustrates how modern pulsar discoveries often rely on a chain of observations across the electromagnetic spectrum. Each wavelength band contributes different pieces of the puzzle. Gamma rays reveal energetic processes near the magnetic poles. Radio pulses provide high-precision timing and a direct measure of the spin, and optical light from the companion traces the binary orbit and the effect of this pulsar's radiation on nearby matter. In the broader context of high-energy surveys, this pulsar stands out as an example of how an initially anonymous point in a gamma-ray map can through patient and methodical work be transformed into a well-characterized neutron star with measured spin and orbit. The high-energy sky thus serves as both a catalogue and a guide, pointing observers to locations where the physics of extreme gravity, dense matter, and strong magnetic fields can be studied in detail. As instruments improve and surveys deepen, more such sources continue to be identified and followed up, enriching the sample of known millisecond pulses and expanding the range of systems in which the interplay of radiation rotation and binary interaction can be explored. Within that growing population, this neutron star occupies a special place discovered through this chain of multi-wavelength observations, and now serving as a key object in studies of the most massive and rapidly spinning neutron stars in the Milky Way. In this system, this neutron star does not move alone through the galaxy, but shares its immediate space with a very low mass companion star bound together in a close binary, whose entire scale would fit easily within the orbit of the innermost planets in the solar system. The separation between the two objects is only a few times larger than the diameter of an ordinary star, so that gravity ties them into an orbit with a period of only a handful of hours rather than days or years. In such a tight configuration, tidal forces shape the companion, pulling it slightly out of a spherical form and stretching it along the line connecting it to this pulsar, while the intense radiation and particle wind from this neutron star constantly strike the side of the companion that faces it. This combination of gravitational pull and high-energy bombardment defines the class of systems known as black widow binaries, in which a rapidly spinning pulsar gradually strips material from a very light companion, reducing its mass over long spans of time. In this case, observations indicate that the companion has only a small fraction of the mass of the Sun, more like a giant planet or a brown dwarf than a full-sized star, even though its composition may resemble that of a star that has lost most of its outer layers. The orbit is nearly circular as expected for systems that have undergone extended phases of mass transfer, and the two bodies move around their common center of mass in a pattern that repeats with precise regularity. From the frame of reference of the companion, this neutron star is an invisible but dominant presence, its gravity controlling the orbit and its radiation heating one hemisphere much more strongly than the other. The side that always faces this pulsar becomes hotter than the far side, leading to a temperature contrast across the surface. This contrast produces the cyclic brightening and dimming seen in optical light curves when astronomers monitor the system over many orbits as the heated face comes into view and then turns away. By modelling this pattern of brightness changes, researchers infer the inclination of the orbit relative to the line of sight from Earth, the size and shape of the companion, and the degree of heating it experiences. Spectroscopic measurements of the companion's motion, in which absorption lines in its spectrum shift back and forth in wavelength as it moves toward and away from the observer, add further constraints. From these shifts, the radial velocity of the companion over the orbit can be traced, and this information combines with the orbital period to yield a mass function that relates the companion mass, the neutron star mass, and the orbital inclination. Because the companion is so much less massive than this neutron star, its motion carries most of the visible signature of the binary's orbital dynamics, while the neutron star's own motion is more subtle but still detectable through changes in the arrival times of its pulses. Radio timing observations record the pulses of this pulsar with such precision that even small changes in distance along the line of sight caused by its orbital motion show up as shifts in pulse arrival time. By fitting these shifts with a model of a binary orbit, astronomers determine the size of the orbit and the projected velocity of this neutron star, and when these timing data are combined with the optical measurements of the companion, the masses of both components can be estimated. In this system, the analysis points to a neutron star whose mass is larger than that of most known pulsars, approaching about 2 1/3 times the mass of the Sun, while the companion carries only a small fraction of a solar mass. This extreme mass ratio is characteristic of black widow systems, in which the pulsar has already accreted substantial material from the companion in the past, and now continues to erode what remains through its wind and radiation. The flow of matter in the system is not in the form of a steady bright accretion disk at the present time, but more as a tenuous outflow from the companion, some of which may be swept away from the system rather than falling onto this neutron star. The interaction region between the pulsar wind and the outflowing material from the companion forms a shock front where particles are accelerated and additional radiation is produced, contributing to the high energy emissions seen from the system. This region is confined within a volume comparable to the size of the orbit, so that the entire binary can be thought of as a compact laboratory where gravity, radiation and plasma flows are tightly coupled. The orbital period being only a few hours means that the system cycles through its configurations many times within a single day, allowing observers to gather large data sets over relatively short spans of observing time. Throughout these cycles, the geometry of the heated and unheated faces of the companion changes with respect to the observer, producing not only brightness variations, but also changes in the spectrum and color of the light. By fitting these details with physical models, astronomers refine their estimates of the companion's size, its temperature distribution, and the fraction of its surface that lies close to the critical boundary where gravity from this neutron star nearly overcomes its own self-gravity. This boundary, known as the Roche lobe, defines the region within which material remains gravitationally bound to the companion. Beyond it, gas can flow outward and be captured by the gravitational pull of this pulsar or driven away from the system entirely. Evidence that the companion in this system nearly fills or slightly overflows its Roche lobe supports the picture in which mass loss is ongoing, or has occurred recently, consistent with the Black Widow scenario of gradual evaporation. On longer timescales, this process can reduce the companion's mass even further, potentially leaving behind only a very low mass remnant or removing it altogether. For the current evolutionary stage, however, the close orbit, the extreme mass ratio, and the pattern of heating and mass loss already reveal a great deal about the binary dynamics. The binary nature of the system is not a minor detail, but a central feature that makes it possible to measure both the orbit and the masses with precision, turning the paired motion of this pulsar and its faint companion into a tool for probing the properties of very dense matter. Around this neutron star, space that would otherwise be quiet is filled with fields and particles driven by rapid rotation and strong magnetism, creating an environment unlike that near an ordinary star. This pulsar has a magnetic field that threads through its interior and extends outward into space, anchored to the crust and rotating together with the star itself. Because the magnetic axis is not perfectly aligned with the rotation axis, the field lines sweep through space as a rotating pattern, and charged particles are forced to flow along them, forming beams and outflows that carry away rotational energy. Near the stellar surface, the magnetic field is so strong that charged particles are confined tightly to narrow tracks, and electric fields induced by the rapid rotation accelerate these particles to high energies. As they move along curved paths, they emit radiation across a wide range of frequencies, including radio waves and gamma rays, and this emission emerges in beams that sweep around with each turn of this pulsar. To a distant observer, the rotation of these beams across the line of sight produces pulses of radiation at a rate set by the spin period, and in this case that period lies in the millisecond range, so that the pulses follow one another hundreds of times each second with regularity. The region around this neutron star can be separated into a magnetosphere, within which the magnetic field dominates the motion of particles, and a broader wind zone in which particles have been accelerated to such high speeds that they stream outward, carrying energy and momentum away. The boundary between regions that co-rotate with this pulsar and those that cannot keep up is known as the light cylinder, defined by the radius at which a point co-rotating with the star would have to move at the speed of light to maintain its angular velocity. Inside this radius magnetic field, lines that are closed guide particles along paths that loop back to the surface, while beyond it open field lines allow particles to escape, forming a wind that extends far into space. The power carried by this wind depends on the spin rate, the strength of the magnetic field, and the rate at which the pulsar's rotation slows, and for a rapidly spinning object like this neutron star, the resulting energy loss can be large. This loss of rotational energy gradually increases the spin period over long timescales, although in the present case the period remains very short, because the star has been spun up in the past by accreting matter from its companion. The magnetosphere is not directly visible as a structure, but its presence is inferred from the observed beams of radiation, the timing of the pulses, and the pattern of high-energy emission. In this pulsar, the high-energy gamma-ray emission suggests that at least some of the radiation arises in regions above the surface, perhaps near the light cylinder, where the combination of strong magnetic fields and rapid rotation efficiently accelerates particles. The particles that escape form a relativistic wind, a flow of electrons, positrons, and possibly heavier ions that streams outward at speeds close to the speed of light. When this wind encounters surrounding material, whether from the interstellar medium or from the companion, it creates a shock front where the flow is slowed and compressed. In an isolated pulsar, this interaction can produce a pulsar wind nebula that glows in X-rays and radio waves, but in a close binary like this one, the main interaction occurs with the outflow from the companion. The side of the companion that faces this neutron star is exposed to high-energy photons and to the pulsar wind, and some of the gas at its surface is heated to the point that it expands and flows away. The pulsar wind meets this outflow and pushes against it, forming a bow-shaped shock that wraps around the companion on the side facing this pulsar. At this shock, particles from the wind are further accelerated and magnetic fields are compressed, creating conditions that can produce additional non-thermal radiation. As the binary orbits, the shape and orientation of this shock region change with respect to the observer, leading to variations in light curves and spectra across different energy bands. The pulsar wind also carves out a cavity in the material around this neutron star, a low-density region, in which the wind dominates the pressure balance. The size of this cavity is set by the balance between the wind pressure and the ram pressure of any incoming gas, and in this system that gas comes primarily from the evaporating companion rather than from the wider interstellar medium. Because the orbit is tight, the interaction region remains within a distance of only a few light seconds from this pulsar, yet within that small volume energy densities and particle fluxes are high compared with typical interstellar conditions. The radiation beams from this pulsar emerge from high altitudes in the magnetosphere and sweep across space, and when the geometry is favourable, Earth lies within the path of these beams, so that radio and gamma-ray pulses can be detected. The detailed shape of the pulses, including their width and relative intensity at different energies, carries information about the locations within the magnetosphere where emission occurs and about the geometry of the magnetic and rotation axes. In addition, when the pulses pass through the material flowing from the companion, they can be scattered, absorbed, or delayed, And these propagation effects produce variations in pulse shape and arrival times that encode information about the density and distribution of plasma in the binary. By monitoring these variations over many orbits, astronomers probe not only the magnetosphere and wind of this neutron star, but also the structure of the evaporating envelope around the companion. In some orbital phases, eclipses of the radio pulses occur when the line of sight passes through dense regions of plasma near the companion or within the shock. These eclipses map out the extent of the absorbing material and show how it changes with time, indicating that the outflow is not perfectly smooth, but may be clumpy or variable. Taken together, these elements define the exterior environment of this neutron star as a system of fields and flows in which the rapid rotation and strong magnetism of this pulsar drive a steady outpouring of energy that shapes its immediate surroundings and plays a central role in the ongoing erosion of the companion star. The surface of this neutron star marks the transition from the familiar behavior of ordinary matter to the extreme conditions that exist deeper inside, and even though the whole star is only a few tens of kilometers across its outer layers, form a structured and active crust. The radius is around 10 to 15 kilometers, yet the mass is a little more than 2 times that of the Sun, so the surface gravity reaches values about 100 billion times stronger than gravity at the surface of Earth. Under such gravity, any irregularity is pressed down with great force, and matter is held so tightly that a grain of dust would be anchored as firmly as a boulder on a planet. A mountain comparable to those on Earth cannot exist here. Even a rise only a few centimeters high carries enough weight that the material must be extraordinarily strong to bear it without flowing. The substance of the surface is thought to be an ultra-dense solid made of atomic nuclei arranged in a crystal-like lattice, immersed in a sea of electrons squeezed into a degenerate state by the immense pressure. In the outermost layer, the nuclei may resemble iron and neighboring heavy elements, the products of nuclear reactions in the progenitor star and in any past accretion. But as depth increases, the pressure grows and electrons are forced into nuclei, changing them into more neutron-rich species. This progression with depth leads to a stratified crust in which composition and density vary smoothly until the density approaches that of nuclear matter and the inner crust merges with the core. For this pulsar, the crust plays a central role in how this neutron star spins, radiates, and responds to its environment. The magnetic field is anchored in currents that flow in the solid and liquid layers, and because the crust is rigid, it carries the field as it rotates, keeping the magnetic axis fixed relative to the solid body, even as this neutron star gradually loses rotational energy. The rapid spin with hundreds of turns each second produces centrifugal forces that slightly flatten this neutron star at the equator, although the change in shape is small compared with the overwhelming pull of gravity. Because the crust is solid, it can store elastic strain. As this pulsar slowly spins down over long timescales, the equilibrium shape that gravity and rotation together would prefer changes, but the solid lattice resists this adjustment. Stresses accumulate as it tries to maintain an older shape while the centrifugal support decreases. When the stress exceeds the breaking strength of the material, parts of the lattice can crack or slip in events sometimes called starquakes, sudden rearrangements that slightly alter the distribution of mass and therefore the moment of inertia. In some pulsars, this shows up as a glitch, an abrupt spin-up superimposed on the smooth slowing trend. Whether this neutron star exhibits such behavior, and if so, how often and how strongly, helps to indicate how rigid its crust is. The thermal state of the surface is another important aspect of the crust. Temperatures may reach hundreds of thousands to millions of degrees Celsius, but because the emitting area is small and the radiation peaks in ultraviolet or soft X-ray bands. The thermal glow is difficult to measure for a distant object in a bright binary. In this system, non-thermal radiation from the magnetosphere and from the shock where the pulsar wind meets the companion's outflow dominates the high-energy emission, yet the underlying heat in the crust still governs how this neutron star cools and how quickly it can conduct energy from inside to outside. The history of this pulsar as an accreting object in the past has likely altered the crust in ways that matter for its present state. During the spin-up phase, gas from the companion flowed onto this neutron star through an accretion disk, funneling along magnetic field lines and striking the surface near the magnetic poles. In those regions, the infalling matter released its gravitational energy as heat and radiation, creating hotspots where nuclear reactions could transform the freshly deposited material. At the high densities in the outer crust, these reactions built up layers of unusual nuclei and released additional heat that slowly diffused outward. Over many cycles of accretion and quiescence, the crust was warmed, compressed, and chemically processed. Even though active accretion has mostly ceased in the current Black Widow phase, the crust still carries the imprint of that history in its composition and thermal profile, and its ability to transmit heat affects any residual thermal emission that might be detectable. General relativity also shapes how the surface appears to distant observers. The strong gravitational field near this neutron star bends the paths of photons leaving the surface so that light from regions near the limb can be deflected toward an observer who would not see them in a simple straight-line geometry. As a result, more than half of the surface is visible at any instant, and hot spots near the magnetic poles, if present, have their apparent brightness and modulation altered by this light bending. In some pulsars, careful modelling of X-ray pulse shapes from such regions yields estimates of the stellar radius. When combined with a measured mass, these estimates provide constraints on the allowed range of dense matter properties. For this pulsar, the high mass inferred from its binary dynamics already shows that the crust and the layers beneath it must support greater pressure than in less massive neutron stars, and any future measurements of its radius would sharpen the constraints on how thick and stiff the crust can be. The crust also acts as the interface between the deep interior and the magnetosphere. Vibrations in the solid lattice, whether triggered by starquakes or by gradual changes in internal stresses, can modulate the currents that feed the magnetic field and may subtly alter the pattern of pulses over time. Long-term timing of this pulsar therefore not only tracks its mean spin down but also samples the response of the crust to forces applied from within and from without, making the surface and crust of this neutron star an active boundary layer that shapes its observable behavior while hiding the still more extreme matter that lies deeper inside. Deep inside, this neutron star matter is compressed to densities that far exceed those found in atomic nuclei, and the familiar distinction between separate atoms no longer applies, so that the interior becomes a continuous medium whose behavior is governed by the strong and weak nuclear forces as well as by gravity. Near the base of the crust, nuclei are packed so closely that their outer regions overlap, and as depth increases further, the transition to the core takes place where individual nuclei dissolve into a fluid of neutrons with a smaller fraction of protons, electrons, and possibly other particles. In this region, the pressure that supports this pulsar against gravitational collapse comes mainly from quantum mechanical degeneracy, in which the Pauli exclusion principle forces particles into higher momentum states as density rises. For typical neutron stars, central densities reach several times the density of nuclear matter measured in laboratory experiments. But for an object as massive as this neutron star, those densities must be higher, still pushing the material into regimes that cannot be reproduced on Earth. The relation between pressure and density in this extreme matter, known as the equation of state, determines how large the star can be for a given mass, and how close it can approach the threshold at which gravity would overwhelm all known forms of pressure and form a black hole. Observations of this pulsar, which indicate a mass of roughly 2 1/3 times the mass of the Sun, already show that the equation of state must be stiff enough to support such a heavy configuration without collapse. If the matter were too soft, meaning that pressure would not rise quickly enough with density, then no stable neutron star could reach this mass, and the object would have collapsed into a black hole at an earlier stage. As a result, this neutron star rules out some proposed equations of state that predict lower maximum masses even though it does not select a single model. Within the core, neutrons may form pairs that move in a coordinated way, producing superfluidity, while protons may also pair and form a superconducting state. These phases change how the star cools, how it responds to small perturbations, and how angular momentum is exchanged between the interior and the crust. In some models, the superfluid component rotates by forming an array of quantized vortices whose collective behavior tracks the overall spin, and interactions between these vortices and the solid lattice of the crust have been proposed as a mechanism for glitches seen in some pulsars. In a very massive object like this pulsar, the balance between superfluid regions and normal nuclear matter may differ from that in lighter stars, and this influences the pattern of cooling and spin evolution, although such properties are difficult to measure directly. At higher densities deeper in the core, additional particles such as hyperons or even deconfined quark matter may appear. These possibilities are supported by theoretical calculations, but the precise conditions under which they would occur inside neutron stars remain uncertain. Introducing such components generally tends to soften the equation of state, reducing the maximum mass that can be supported. Therefore, the existence of this neutron star with its high mass implies that if exotic phases like hyperons or quark matter are present, their contributions must be balanced in a way that does not overly reduce the pressure. This requirement places constraints on the microphysics of dense matter, but the allowed range is still broad. Measurements of the star's radius, if obtained with sufficient precision, could combine with the known mass to narrow down the allowed equations of state further, because different models predict distinct mass-radius relations. For now, the high mass serves as a strong filter, eliminating some scenarios while leaving others viable. The rapid rotation of this pulsar adds another layer to the interior physics. With a spin frequency of several hundred turns each second, centrifugal forces reduce the effective gravity at the equator, compared with the poles, slightly changing the density profile and the shape of the star. This rotational flattening, though small, compared with the overall size, affects the equilibrium structure, and must be taken into account when calculating how close the configuration lies to the maximum mass limit. In addition, rapid rotation allows for non-radial oscillation modes that are influenced by the Coriolis force and can emit gravitational waves that carry away angular momentum. Whether such instabilities operate in this pulsar depends on details of the interior viscosity and superfluid properties and remains an open research question. Neutrinos, nearly massless particles that interact only weakly with matter, provide another channel for energy loss. In young neutron stars, neutrino emission from reactions in the core dominates the cooling for long periods. In very massive stars like this, neutron star central densities may be high enough to allow more rapid processes, and if such fast cooling operates, the interior temperature drops more quickly, affecting the thermal gradient between core and crust. For this pulsar, which has already passed through its earlier stages and undergone a long history of accretion and spin-up direct observation of the core temperature, is not feasible, but different assumptions about neutrino cooling lead to distinct long-term thermal histories. All these elements together mean that the interior of this neutron star serves as a natural laboratory for physics that cannot be tested in terrestrial experiments. Its high mass restricts the equation of state to a subset of relatively stiff possibilities. Its rapid spin pushes rotational models into regimes where centrifugal deformation and oscillation modes matter, and its dense core may or may not host exotic particles or phases whose signatures would subtly influence observable quantities. While current measurements do not yet resolve all these questions, they show that this pulsar occupies a region of parameter space where the interplay between gravity nuclear forces and quantum statistics reaches some of its most extreme known conditions, and ongoing and future observations aim to refine its mass, constrain its radius, and further illuminate the properties of dense matter inside this neutron star. The interior structure of this neutron star is not observed directly, yet the combination of its high mass and rapid spin allows scientists to infer limits on how matter behaves at densities beyond those reached in atomic nuclei. In general relativity, the balance between gravity and pressure is described by equations that connect the mass and radius of a star to the relation between pressure and density in its interior. For a given equation of state, this balance yields a maximum mass, above which no stable neutron star configuration exists, and collapse to a black hole becomes unavoidable. The measured mass of this pulsar, inferred from the dynamics of its binary companion, lies close to or above the lower edge of many predicted maximum masses, so the continued existence of this neutron star as a compact star rather than as a black hole means that those softer models of dense matter cannot describe reality. In practical terms, this removes from consideration a range of theories in which the pressure at high density rises too slowly, including some that introduce additional particles that tend to soften the equation of state. At the same time, there remain families of models that are stiff enough to allow a star with this mass to remain stable, and distinguishing between them requires observables beyond mass alone. One such observable is the radius which responds sensitively to the pressure at densities around and somewhat above that of ordinary nuclear matter. For two stars of similar mass, a stiffer equation of state generally produces a larger radius, while a softer one leads to a more compact star. In principle, measurements of X-ray emission from hotspots on the surface, combined with models that include the bending of light by the gravitational field, can yield constraints on the radius, because the apparent size and modulation of the emitting regions depend on the ratio between mass and radius. For this pulsar, however, the presence of strong non-thermal emission from the magnetosphere and from the shock in the binary makes it challenging to isolate any thermal surface component, so radius estimates remain uncertain. Massive neutron stars like this neutron star are particularly valuable because they probe the high-density end of the relation between pressure and density, where differences between models become more pronounced. Observations of other heavy pulsars with masses close to 2 times that of the Sun already demonstrate that dense matter must be capable of generating significant pressure at several times nuclear density. The even higher mass inferred for this pulsar strengthens this conclusion, pushing the allowed region towards stiffer behavior and leaving less room for models that predict an early onset of exotic components that would greatly reduce the pressure. At the same time, observations of neutron star mergers through gravitational waves provide complementary information about how easily stars deform in response to tidal forces. The tidal deformability depends on the same equation of state that governs isolated stars, and measurements from mergers deepen the constraints on the relation between pressure and density. When these data are combined with the known mass of this neutron star, researchers can test whether a single equation of state can account for both the properties of heavy, rapidly spinning pulsars and the behavior of stars in merging binaries. Rapid rotation itself modifies the internal equilibrium, and this pulsar spins so quickly that rotational effects cannot be ignored in detailed models. A rotating neutron star can support slightly more mass than a non-rotating one, with the same equation of state, because centrifugal forces reduce the effective gravity, especially near the equator. This increase in the maximum supported mass depends on the spin rate and the internal structure, so when interpreting the mass of this neutron star, models must account for its rotation. Calculations that include rotation show that for spin frequencies of several hundred turns each second, the allowed increase in maximum mass is significant, but not sufficient to rescue equations of state that otherwise fail by a large margin. Thus, the high mass of this pulsar still favors relatively stiff behavior of dense matter, even when its rapid rotation is taken into account. The internal composition and phase structure of this neutron star also affect its moment of inertia, which determines how much angular momentum it carries for a given spin rate. If the equation of state is stiff, the star tends to be larger and to have a greater moment of inertia than a softer star of the same mass. Precise timing of this pulsar over long intervals measures how quickly its rotation slows and how much rotational energy it is losing to radiation and particle winds. When combined with estimates of the magnetic field strength and the geometry of the magnetosphere, these spin-down measurements can provide indirect clues about the moment of inertia and thus about the internal distribution of mass and pressure. Although uncertainties in the magnetic and geometric parameters currently limit the precision of such inferences, future observations may refine them enough to extract tighter constraints. Another set of potential probes involves oscillation modes of the star, which can, in principle, emit continuous or transient gravitational waves. The frequencies and damping times of these modes depend on the equation of state and on the distribution of superfluid and superconducting components in the interior. For now, no persistent gravitational wave signal from this pulsar has been detected, and the upper limits from searches already place bounds on how large such deformations can be. If a signal were found in the future, it would offer a new window into the interior, similar in spirit to the way that seismology reveals the inside of Earth. Even without such detections, the fact that this neutron star exists with its measured mass and spin places it in a small but important class of objects that test the limits of dense matter physics. Each refinement in its measured parameters, each new constraint from timing spectroscopy or high-energy observations will further tighten the allowed range of equations of state. In this way, this pulsar serves as a bridge between astrophysical observation and fundamental nuclear physics, its compact interior holding information about interactions at densities and energies that would be unreachable in any laboratory experiment, while its observable properties translate that hidden structure into signals that can be measured and interpreted from across the galaxy. The high mass assigned to this neutron star does not come from a single type of observation, but from a careful combination of several measurements, each with its own uncertainties, and the way these pieces fit together helps to define how strongly this pulsar constrains dense matter physics. In the binary, the companion's orbit is traced both by changes in its radial velocity, measured through shifts in spectral lines, and by the periodic brightening and dimming of its heated surface seen in optical light curves. From the radial velocity curve, astronomers derive how fast the companion moves toward and away from Earth over an orbit, while the light curve encodes the inclination of the orbit and the temperature contrast across the companion's surface. Together, these data yield a mass function that relates the mass of this neutron star to the mass of the companion and the orbital tilt. Because the companion is so light compared with this pulsar, and because the orbit is nearly circular, small changes in the assumed inclination can significantly alter the inferred mass of this neutron star. Models of the optical light curve attempt to break this degeneracy by reproducing the observed amplitude and shape of the brightness variations, which depend sensitively on how much of the heated hemisphere is visible at different orbital phases. To do this, researchers must assume or infer the companion size, its surface reflectivity, and the efficiency with which it reprocesses the intense irradiation from this pulsar into observable light. These ingredients introduce systematic uncertainties, but even when a range of plausible values is considered, the derived mass of this neutron star remains high, near, or above about 2 1/3 times the mass of the Sun. Radio timing adds further constraints. The arrival times of the pulses from this pulsar shift slightly as it moves around the binary orbit, producing a timing curve that reveals the projected size of its orbit and the mass ratio between the two components. When this is combined with the optical motion of the companion, the internal consistency of the binary model can be checked, and any mismatch would signal that some assumption needs revision. For this system, the timing and optical data support a solution in which this neutron star is heavier than most others known. At the same time, researchers remain cautious and explore alternative models, asking how changes in inputs such as the companion's atmosphere, the distribution of heating, or the presence of spots might shift the mass estimate. The result is a range of possible masses rather than a single exact value, but even the lower end of this range lies near the upper edge of the neutron star mass distribution measured in other systems. In the broader sample of neutron stars with well-measured masses, many objects in double neutron star binaries cluster around values close to 1 1/2 times the mass of the Sun, while some in X-ray binaries and millisecond pulsar systems reach, or slightly exceed, about 2 solar masses. This pulsar appears above that cluster, in a region where relatively few objects are found, so its presence indicates that nature can assemble and support neutron stars at masses at least this high. Because the underlying equation of state must allow all observed neutron star masses, this neutron star pushes the required stiffness at high density, further than systems with lower mass values. Black widow systems as a class play an important role in this context because they often host recycled pulsars that have accreted significant mass from their companions. During the earlier accretion phase, material spiraled onto this neutron star through a disk, transferring angular momentum and spinning it up to its present high frequency, while also adding to its mass. The total amount of mass accreted depends on the duration and rate of this phase, which are not directly observed but can be estimated from population studies and from models of binary evolution. If this pulsar indeed has a mass well above 2 solar masses, then the combination of its initial birth mass and the subsequent accreted mass must have been sufficient to reach that value without crossing the stability limit and collapsing into a black hole. This requirement places additional constraints on how massive neutron stars are at birth and how much mass transfer they can tolerate. It also raises the question of whether some recycled pulsars might sit even closer to the true maximum mass, rotating rapidly enough that centrifugal support helps keep them stable. In such a case, gradual spin down over very long timescales might eventually bring the star to a point where no equilibrium configuration exists for its mass, and reduced spin and collapse could occur. Whether this scenario applies to this neutron star depends on the detailed form of the equation of state, and on how far its current mass and spin lie from any instability boundary, and at present these aspects remain under active study. The measurements of this pulsar thus illustrate a general pattern in the study of dense matter. Observations provide values and ranges for quantities like mass spin and, when possible, radius. Theoretical models of neutron star structure translate each proposed equation of state into predictions for these quantities, and comparison between the two allows models to be ruled out or retained. A single object rarely decides the issue on its own, but an object that sits at an extreme like this neutron star exerts a strong influence, because any viable theory must accommodate it. When combined with information from other heavy pulsars from gravitational wave events involving neutron stars and from laboratory experiments on nuclear matter, at lower densities the data from this pulsar help to carve out an allowed region in the space of possible equations of state. Each refinement in the optical modelling of the companion, each improvement in radio timing precision, and each new high-energy observation that clarifies the geometry and environment of this pulsar reduces the uncertainties in its fundamental parameters. In this way, the binary that hosts this neutron star is not only an astrophysical system in its own right, but also a precise measuring tool. Its orbital motion irradiated companion and rapidly spinning primary act together to encode information about the maximum mass that neutron star matter can bear. Decoding that information requires careful treatment of both observational and theoretical uncertainties, and future work aims to sharpen both. But even now, this pulsar stands as one of the clearest examples of how a single compact star and its faint, nearly eroded companion can inform the physics of matter at densities far beyond anything directly attainable on Earth. The combination of high mass and rapid spin in this neutron star also places it in a regime where rotational limits become important, because for any given equation of state there exists a maximum spin rate beyond which matter at the equator would no longer remain gravitationally bound. This threshold, sometimes described as the mass-shedding limit, depends on how the star's radius and internal pressure respond to gravity, so that a heavier star with a small radius approaches the limit at a different spin rate than a lighter, larger star. In practice, calculations that include general relativity and realistic equations of state show that the maximum allowed spin for a neutron star of a few times the mass of the Sun lies at several hundred, to perhaps over 1,000 turns each second, with the precise value varying from model to model. This pulsar with a spin of several hundred turns each second lies below this limit, but close enough that the difference between models matters. If the equation of state were too soft, leading to an especially compact configuration for a given mass, the allowed maximum spin would decrease, and a star rotating as fast as this neutron star might not remain stable. The fact that it does spin stably at this rate therefore supports models in which the star is not excessively compact for its mass, which again favours relatively stiff behaviour at high density. Rotational effects also change the distribution of density inside this pulsar, making it slightly ablate with matter at the equator, experiencing a lower effective gravity than matter near the poles. This differential influences how internal oscillation modes behave and how angular momentum is transported between different layers. In rapidly rotating neutron stars, certain families of oscillation modes can become unstable through the emission of gravitational waves if the internal viscosity and superfluid properties fall within particular ranges. These instabilities would act as a brake on the spin, preventing stars from reaching or maintaining very high rotation frequencies. The presence of this neutron star and other fast-spinning millisecond pulsars suggests that either these instabilities are suppressed perhaps by viscous damping, or by particular superfluid characteristics, or that the stars evolve in such a way that they skirt the regions of parameter space where the instabilities are strongest. Although no continuous gravitational wave signal has been detected from this pulsar, the very fact that it spins so rapidly without obvious signs of dramatic spin down implies that any unstable modes must either be weak or heavily damped. This inference feeds back into models of the interior because different assumptions about superfluid pairing, mutual friction between vortices and the normal component, and the viscosity of dense matter lead to different predictions for how easily these modes can grow. Spin-down measurements provide another observable link to the interior. The rotation of this pulsar gradually slows over time as it loses energy through electromagnetic radiation and the acceleration of particles in its wind. The rate of change of the spin period when combined with the period itself yields a characteristic timescale and an estimate of the total rotational energy being lost. For a given magnetic field, strength and geometry, this energy loss connects to the moment of inertia, which depends on how mass is distributed inside this neutron star. A stiffer equation of state tends to produce stars with larger radii and greater moments of inertia, which in turn affects how the observed spin down translates into magnetic field strength and energy output. Although uncertainties in the magnetic inclination and the distribution of currents in the magnetosphere introduce ambiguity, analyses that explore broad ranges of these parameters can still place statistical constraints on the moment of inertia and therefore on the internal structure. For this pulsar, whose high mass already restricts the set of allowed equations of state, any future refinement in spin-down measurements could add a complementary constraint that further narrows the range of possibilities. The thermal history of this neutron star also depends on its interior composition, even if direct measurements of its surface temperature are difficult. In dense matter, neutrino emission from reactions involving neutrons, protons, electrons, and any additional particles provides an efficient cooling channel. Different compositions and superfluid states either enhance or suppress these neutrino processes, altering the rate at which the core loses heat over hundreds of thousands to millions of years. A very massive neutron star like this neutron star may reach central densities high enough to permit faster neutrino processes than those available in lighter stars, which would tend to cool it more quickly. If the crust and core are coupled strongly, the surface temperature would respond to this cooling, while, if they are more weakly coupled, temperature gradients could persist. When thermal emission is observable from other neutron stars, comparisons between their ages, temperatures, and masses provide clues about which cooling processes are active, though direct thermal measurements for this pulsar are hampered by its bright non-thermal emission, and binary environment theoretical models of its cooling matched to its known mass, and spin must remain consistent with the general patterns seen in the wider neutron star population. In this way, even an object whose surface heat is not directly measured still influences the acceptable region of parameter space for dense matter composition and superfluid properties. Another aspect of interior physics involves the coupling between the superfluid component of the core and the solid crust. In some pulsars, sudden changes in the spin period known as glitches are interpreted as episodes in which angular momentum stored in the superfluid is transferred abruptly to the solid crust as vortices unpin and move. The size and frequency of such events depend on how many vortices are pinned, how strong the pinning is, and how stresses accumulate. For this neutron star, long-term timing studies search for any deviations from the smooth spin-down curve that might indicate similar events. If glitches are rare or absent, this may suggest that the coupling between core and crust in this particular star differs from that in glitching pulsars, possibly because of its different mass spin rate or magnetic environment. Such differences would need to be reflected in microscopic models of vortex pinning and superfluid dynamics, again connecting observable timing behavior to the physics of matter at high density. Overall, the interior region of this pulsar remains hidden from direct view, yet its global properties and time-dependent behavior translate that hidden structure into constraints that can be compared with theoretical models. High-mass rapid spin-stable rotation below but near theoretical limits, and spin-down rates consistent with sustained energy loss through electromagnetic and particle channels all point to a core in which pressure rises rapidly, with density superfluid and superconducting phases likely exist, and possible exotic components must arrange themselves in a way that preserves enough stiffness to support the observed mass. Every additional neutron star observed with similarly extreme properties would refine this picture, but even standing alone, this neutron star occupies a corner of parameter space, where the combined requirements of stability rotation and cooling leave only a limited set of dense matter behaviors that can be considered compatible with the evidence. The story of this neutron star as a probe of dense matter begins with its birth in a supernova and continues through the period of mass transfer that spun up this pulsar, and each stage leaves an imprint on the interior that theory must consider when interpreting its present mass and spin. When a massive star exhausts the nuclear fuel in its core, fusion can no longer balance gravity, and the core collapses inward, squeezing matter to densities at which electrons and protons combine into neutrons. The sudden halt of this collapse, when repulsive components of the nuclear force and neutron degeneracy pressure become dominant, launches a shock wave that, together with neutrino heating, expels much of the outer layers of the star. The remnant is a hot rotating proto-neutron star whose mass depends on how much material falls back. In the earliest moments, this newly formed neutron star cools mainly by emitting neutrinos, and its interior settles into a configuration set by the equation of state at high density. If the total mass exceeds the maximum allowed by that equation of state collapse to a black hole follows, if not the star survives. For this pulsar to exist today with such a high mass, the combination of its birth mass and any accreted material must have remained below the true maximum at all times, and this already eliminates models in which even moderately heavy neutron stars are unstable. After birth, this neutron star did not always spin hundreds of times each second. Like other millisecond pulsars, it is thought to have been recycled in a low-mass X-ray binary phase, during which gas from a companion star overflowed its Roche lobe and formed an accretion disk. Over long periods, viscous processes in the disk transported angular momentum inward, and material spiraled down along magnetic field lines to strike the surface, transferring spin and mass. The rate at which angular momentum was added and the total amount of mass transferred depended on the accretion history, which is not observed directly, but can be sketched from binary evolution models. In these models, the interior of this neutron star responds to the added weight, by pushing matter in the core to higher densities and altering the balance between its components. If exotic particles or phases are possible at some threshold density, the gradual increase in central density during accretion provides an opportunity for the core to cross that threshold. If such components appear and greatly soften the pressure response, the star may approach instability. If the equation of state remains stiff enough, the star can accommodate the additional mass without collapsing. Thus, the existence of this pulsar as a stable, very massive, rapidly rotating neutron star implies that whatever internal changes occurred during its accretion history did not push it beyond the stability boundary. The process of spin-up also affects the distribution of angular momentum within the star. As the surface layers are forced to rotate faster by the inflowing material, internal torques transmit angular momentum inward, and over time the interior adjusts toward nearly uniform rotation. Superfluid components in the core, if present, carry angular momentum through quantized vortices, and the motion and pinning of these vortices against the lattice in the inner crust mediate the coupling between different regions. For this neutron star, the final rotation rate of several hundred turns each second indicates that this redistribution of angular momentum reached a configuration in which the star from crust to core participates in the rotation closely enough that the observed pulses are stable over long periods. Any internal differential rotation that remains must be small enough not to produce large, easily detected timing irregularities. When accretion subsides and the system evolves into the present Black Widow state, the disk dissipates and the magnetosphere of this pulsar reasserts itself, driving a wind that erodes the companion. Within this neutron star, the end of accretion alters the thermal and compositional evolution of the crust. Accretion heated the crust through nuclear reactions in dense outer layers, and over time that heat diffused into the core and was radiated away as neutrinos and photons. Once accretion stops, the crust cools and may relax toward a different equilibrium, potentially changing the pattern of superfluid pairing and the strength of crustal currents that anchor the magnetic field. The high mass of this neutron star means that its core pressure remains great, and the structure established during its accretion era continues to determine how it responds to further slow changes. Any theory that seeks to explain the current interior state must therefore reproduce not only a static configuration with the observed mass and spin, but also a plausible path from birth through spin up to the present. Population studies of millisecond pulsars and Black Widow binaries show that many recycled pulsars have masses only slightly above those of birth values in non-recycled systems, while a subset, including this neutron star, appear to have gained substantial mass. For dense matter models, this variation is important because it indicates that neutron stars can be pushed toward high masses without inevitably collapsing so long as the equation of state provides enough pressure at the relevant densities. The presence of this pulsar near the upper end of the observed mass range indicates that at least some neutron stars can survive extreme accretion histories. At the same time, the absence so far of confirmed neutron stars with masses far above that of this neutron star suggests that there is a real maximum not much higher beyond which stability fails. This pattern of existence and absence feeds into efforts to map out the allowed equations of state. Models that would permit neutron stars with arbitrarily high masses are disfavored, while those that cap the maximum near or somewhat above the mass of this pulsar remain viable. Thus, the life story of this neutron star from core collapse through spin-up to its present role in a Black Widow system forms a chain of physical processes that has tested dense matter at each step. The fact that it passes all of these stages without collapsing means that the true equation of state must support a path through this history, and any description that cannot accommodate such an object must be set aside in favor of those that can, making this pulsar a stringent benchmark for models of matter at the highest densities known in the observable universe. In studies of dense matter, this neutron star stands alongside other heavy pulsars and compact stars as one point in a growing map of how pressure behaves at very high density, and its particular combination of properties shapes the part of that map that lies at the high mass rapid spin corner. Observers use its measured mass as one axis on this map and seek other quantities that can define additional directions, such as radius moment of inertia, tidal deformability and cooling behavior. For some neutron stars, tidal deformability is inferred from gravitational wave signals produced when two such stars spiral together and merge, but this pulsar currently orbits a much lighter companion, so no such measurement is available. Instead, its role is to mark the boundary of how massive a stable neutron star can be, while still rotating hundreds of times each second a role that complements the information gained from mergers of somewhat less massive stars. Theoretical models integrate all these constraints at once. In one corner of the parameter space lie equations of state that are very stiff, predicting large radii and high maximum masses. In another lie softer models that yield more compact stars and lower maxima. The existence of this neutron star pushes the allowed region toward the stiff side, but observations of tidal deformability from mergers encourage some compactness, so models that survive must thread a path between these tendencies. In practice, this means that pressure must rise quickly enough with density to support this pulsar, but not so quickly at lower densities that typical neutron stars become too large compared with what gravitational wave data suggest. Researchers explore these requirements by adjusting parameters that describe interactions between nucleons, the contribution of three body forces, and the behavior of the symmetry energy that expresses how pressure changes as the ratio of neutrons to protons varies. Laboratory experiments with heavy ion collisions and measurements of nuclear structure provide information about these parameters at densities around or below that of normal nuclei, but the densities in the core of this neutron star can be several times higher, so extrapolation is needed. The degree to which different extrapolations can match both terrestrial and astrophysical data is one way to assess which equations of state remain viable. Within this framework, this neutron star acts as a distant but powerful data point one that cannot be reached by any beam or detector on Earth, but that still influences how nuclear physics is formulated. Another direction in which this pulsar informs dense matter physics concerns the possible presence of exotic components. Many theoretical models predict that at sufficiently high density, new degrees of freedom become energetically favorable. Hyperons, which are baryons containing strange quarks, may appear as additional species. Meson condensates or deconfined quark matter could form in the deepest regions. Each of these possibilities tends to soften the equation of state if introduced without compensating mechanisms, because they allow matter to rearrange itself into more states without a proportionate increase in pressure. If such components appeared in abundance at densities reached in the core of this neutron star, they would likely reduce the maximum mass below the observed value. To keep this pulsar stable, models that include exotic matter must introduce additional repulsive interactions or other stiffening effects at high density. In this sense, the interior of this neutron star tests not only whether exotic phases are possible, but also how strongly particles in those phases must repel each other. While current observations cannot determine directly whether the core contains hyperons quark matter or only nucleons and leptons, they delineate what combinations of these ingredients and their interactions could be present. The rapid spin of this pulsar adds yet another angle to the constraint picture. In principle, a very rapidly rotating neutron star has higher centrifugal support at the equator, which can allow a slightly higher maximum mass than a non-rotating configuration. For this neutron star rotating hundreds of times each second, that additional support is significant but not dominant. Detailed calculations that include rotation show that the maximum mass can increase by perhaps a few tens of % depending on the equation of state. If the true non-rotating maximum mass lay only slightly above 2 times, the mass of the Sun rotational support might be necessary to sustain this neutron star. On the other hand, if the equation of state is stiff enough that even a non-rotating star could reach or exceed its mass, then rotation provides a margin of safety rather than a requirement. Distinguishing between these cases requires both accurate knowledge of the mass and precise modelling of rotational effects. Should future observations refine the mass upward or downward, the balance between rotational support and intrinsic stiffness would shift, and the intersection of allowed models would move accordingly. The uncertainties in current mass estimates in turn translate directly into a band of allowed behavior for dense matter, rather than a single curve. From a broader perspective, this pulsar is one of several objects that cluster near the high mass end of the neutron star population, and together they form a small but influential group that constrains the top of the mass-radius relation. Below them, a wide distribution of neutron stars of more ordinary mass fills in the relation at lower densities, while gravitational wave observations probe combinations of mass and tidal deformability. In this combined landscape, this neutron star helps to anchor the upper boundary, making it harder for any proposed equation of state to deviate strongly from stiff behavior at high density without contradicting at least one observational datum. As more data accumulate both from this system and from others, like it, the patch of parameter space that remains consistent with all observations shrinks, and within that shrinking patch, the interior of this neutron star sits as one realization of matter, arranged under extreme compression, its properties silently encoded in the way it spins, cools, and holds itself up against its own gravity. The interior of this neutron star continues to serve as a focus for testing how matter behaves when compressed beyond ordinary nuclear density, and the questions that remain about its core guide both observational campaigns and theoretical work. One basic question concerns how sharply the properties of dense matter change with depth inside this pulsar. In some equations of state pressure and composition vary smoothly as density rises with neutrons, protons, and leptons, adjusting their proportions without abrupt transitions. In others, the material may undergo phase changes in which new components appear, or the arrangement of particles reorganizes in a more sudden way, such as the onset of hyperons or the conversion of nucleons into deconfined quarks over some range of densities. These possibilities imprint themselves on macroscopic quantities like radius moment of inertia, and how the star responds to compression or tidal forces, but they do so in subtler ways than the overall maximum mass. Because this neutron star sits near the upper end of the allowed mass range, its core extends into density regimes, where such transitions, if they occur at all, within neutron stars are more likely to appear. One line of investigation asks whether there could be a relatively soft layer at intermediate densities sandwiched between stiffer behavior at lower and higher densities, so that stars of around average mass remain more compact, while very heavy stars such as this neutron star still gain enough pressure at the highest densities to avoid collapse. In this picture phase, changes or new components might appear and then be followed by additional stiffening due to repulsive interactions at still greater densities. Another line of work uses parameterized families of equations of state, in which the relation between pressure and density is described by a set of adjustable parameters that can be tuned to match laboratory data at low density and astrophysical constraints at high density. In such studies, this pulsar acts as a boundary condition. Any combination of parameters that fails to support a star at its mass is ruled out. As more observational inputs are added, such as typical radii inferred for neutron stars of around 1 1/2 times the mass of the Sun tidal deformabilities from mergers and cooling behavior, the allowed volume in parameter space shrinks, and the region that survives must be consistent with the existence of this neutron star as well as with the rest of the neutron star population. Future observations could sharpen this picture further. If instruments sensitive to X-rays can isolate even a weak thermal signal from the surface of this pulsar and measure its modulation over a rotation-detailed modeling that includes light bending, and the geometry of hot regions could yield a constraint on its radius. Combined with its already high mass, such a radius would pick out a narrower band of equations of state. If gravitational wave detectors were ever to sense a continuous wave from a small stable deformation, In this neutron star or a transient signal associated with a star quake or other internal event, the frequency and amplitude of that signal would offer an independent probe of the interior. Even if such detections remain beyond current capabilities, the absence of strong signals already places upper limits on how large any persistent distortion can be. Observations across the electromagnetic spectrum also continue to refine the parameters of the binary. Improved optical spectroscopy can reduce uncertainties in the velocity curve of the companion and in its atmospheric properties, while more precise photometry can better trace the detailed shape of its light curve, including any asymmetries or spots that might affect the inferred inclination. On the radio side, longer timing baselines and higher precision measurements can tighten constraints on orbital parameters and spin down, perhaps revealing subtle secular changes that trace the loss of angular momentum. Each refinement feeds back into the estimate of the mass of this neutron star, and into the understanding of how close it lies to any rotational or stability limits. On the theoretical side, advances in calculations of dense matter, using methods rooted in quantum chromodynamics and effective field theory, seek to extend reliable predictions to higher densities while quantifying uncertainties. These approaches aim to connect the microphysics of interacting nucleons and quarks to the macroscopic properties of neutron stars, so that constraints from objects like this pulsar feed directly into the underlying theory of the strong force. At the same time, simulations of neutron star structure that include both rotation and realistic equations of state continue to map out the range of possible configurations, identifying which combinations of mass radius and spin are compatible with stability. In such simulations, this neutron star appears as a point in the space of solutions that must be reproduced, and its existence limits how sharply properties can vary with density. It also pushes models to handle the interplay between rotation, composition, and superfluidity in a regime where all three are important. In addition, studies of cooling and heating in massive neutron stars explore how ongoing particle reactions and superfluid pairing in the core affect the long-term thermal evolution, with an eye toward matching the behavior of stars that can be observed more directly in X-rays. Even though this pulsar's own thermal emission is not yet well measured, any viable model must allow a thermal history for such a massive recycled neutron star that fits within the broader pattern. In this way, the interior of this neutron star acts as both a test and a guide, indicating where extrapolations of nuclear physics to high density must be cautious and where they can be more confident and motivating new observations that might reduce uncertainties and reveal more about how this compact object holds itself together under such extreme conditions over spans of time far longer than any human experiment. As constraints tighten, the set of equations of state cooling scenarios and internal compositions still compatible with this pulsar slowly contracts, turning this single, distant neutron star into a long-term benchmark against which ideas about dense matter will continue to be measured. This neutron star also plays a role in connecting the physics of dense matter to other branches of astrophysics, because its existence influences how scientists interpret events in which neutron stars collide, merge or collapse, and these larger-scale processes depend sensitively on the maximum mass that dense matter can support. When two neutron stars spiral together and merge, the mass of the remnant temporarily exceeds that of either progenitor, and whether the remnant promptly collapses to a black hole or survives as a massive differentially rotating neutron star for some time depends on the equation of state. Observations of such mergers through gravitational waves and electromagnetic counterparts suggest that in some cases the remnant persists long enough to drive energetic outflows, while in others collapse appears to be rapid. The value of the maximum mass inferred from these events must be consistent with the mass of this neutron star, because the same dense matter, physics governs both isolated stars and merger remnants. If the maximum mass were only slightly above 2 times the mass of the Sun, then a neutron star as heavy as this neutron star would be difficult to maintain in a stable state, especially once rotational support is taken into account. The fact that this pulsar exists as a long-lived, rapidly spinning object therefore sets a lower bound on the maximum mass that merger remnants can attain before collapsing, and this in turn feeds into models of how long they can power electromagnetic emission and how much mass they can eject. In population synthesis studies where large numbers of binary star systems are simulated over cosmic times to predict how many neutron stars a merger should exist, the equations of state used to determine which remnants become neutron stars and which become black holes must respect the constraint provided by this neutron star. If the maximum mass is set too low, many simulated systems would produce black holes instead of neutron stars at birth or after accretion, which would conflict with the observed presence of very heavy pulsars. Setting the maximum mass high enough to allow this neutron star to survive shifts, the outcomes increasing the fraction of binaries that pass through phases similar to the accretion history of this pulsar and end up as millisecond pulsars with light companions. Thus, the internal physics of this neutron star subtly shapes predictions about the demographics of compact objects in the galaxy. On smaller scales, the composition and stiffness of the core influence how this pulsar responds to small perturbations and to ongoing torques. In a star with a relatively soft core, differential rotation and oscillation modes could persist more easily, while in a stiff core restoring forces are stronger and might suppress some instabilities. This neutron star must have avoided catastrophic instabilities during and after its spin-up because its present rotation remains stable and its pulse profile is regular. Models of R-mode oscillations, which can be driven unstable in rapidly rotating stars and emit gravitational waves, must therefore allow conditions in which such modes are damped strongly enough for this pulsar not to lose its spin quickly. This requirement again ties back to interior composition, viscosity and superfluid properties. If the core contains deconfined quark matter, for example, the damping rates and allowed mode amplitudes might differ from those in a purely nucleonic core, and any such differences must be arranged so that this neutron star can maintain its rapid spin over long timescales without producing gravitational wave signals stronger than current upper limits. In addition, the way in which this neutron star exchanges angular momentum between its core and crust during small spin irregularities, if any occur, depends on the mobility of quantized vortices in the superfluid and their interaction with the lattice in the inner crust. Even if timing observations have not yet revealed clear glitches for this pulsar, the absence of large events places constraints on how easily vortices unpin, and on how much angular momentum can be stored in the superfluid reservoir given the star's high mass and internal density profile. Cooling behavior provides yet another connection. In less massive neutron stars, the dominant neutrino emission processes in the core might be relatively slow, leading to gradual cooling over hundreds of thousands of years. In very massive stars like this, neutron star central densities may open up faster neutrino processes that cool the core more quickly, lowering the internal temperature at a given age. Although the thermal emission from this pulsar is not directly measured with high precision, any acceptable cooling scenario for dense matter must allow the existence of such a massive recycled neutron star that has undergone an accretion phase and then settled into a long-lived, rapidly spinning state without conflicting with the general pattern of observed neutron star temperatures. This motivates models in which superfluidity and superconductivity in the core regulate neutrino processes, sometimes suppressing them and sometimes enhancing them at particular densities, so that stars of different masses follow different cooling tracks. In that context, this pulsar would follow a track appropriate for a very massive older accretion-heated neutron star. And while its exact position on such a diagram is not yet known, the mere fact that such a track must exist influences how theorists adjust parameters in their models. On a more observational side, this neutron star also pushes instruments and analysis techniques to their limits, driving improvements that benefit the study of dense matter more broadly. High-precision timing of this pulsar requires stable receivers' careful calibration and long baselines, and the timing solutions derived from it help test how well clocks, ephemerides, and data reduction pipelines perform. Any small systematic errors in timing would propagate into the derived orbital parameters and mass. Consequently, efforts to reduce such errors sharpen not only the measurements for this pulsar, but also for many others used in pulsar timing arrays and related projects. In optical and high-energy bands, modeling the light from the irradiated companion in this binary demands detailed understanding of stellar atmospheres under unusual conditions where one hemisphere is strongly heated by a nearby pulsar. Improvements in such models assist not only in refining the mass of this neutron star, but also in interpreting similar systems across the Black Widow population, many of which host heavy pulsars that jointly constrain the dense matter equation of state. In this way, the interior physics of this neutron star and the observational techniques used to probe it are intertwined. The extreme nature of this pulsar demands careful observations, which in turn drive advances in instrumentation and theory, and these advances feed back into a clearer picture of what kinds of matter and interactions can exist at the densities and pressures found in the core of this neutron star. Over time, as data accumulate and models improve, the range of possible descriptions narrows, and the point on the mass spin plane occupied by this pulsar becomes ever more tightly linked to a specific band of equations of state-making. This neutron star, not just an outlier, but a cornerstone in the ongoing effort to understand matter under the most intense compression found in the observable universe. Among the known neutron stars in the Milky Way, this neutron star occupies a distinctive position, not only because of its high mass and rapid spin, but also because it belongs to the class of Black Widow systems, and this combination links the physics of dense matter to the long-term evolution of compact binaries. Surveys of the galaxy in radio gamma ray and X-ray bands reveal many millisecond pulsars, some isolated, and some in binaries with white dwarf companions, low-mass stars, or very light, strongly irradiated objects like the companion in this system. Black widows and related systems known as redbacks share the feature that a pulsar wind and high-energy radiation ablate their companions, gradually reducing the companion mass and in some cases nearly removing it. In these systems, this pulsar has already passed through an accretion phase in which it was spun up and may have gained significant mass. As a result, Black Widow pulsars are natural candidates to host some of the heaviest neutron stars, and this pulsar with a mass estimate above 2 times that of the Sun reinforces this expectation. Population studies that compare the properties of Black Widow's redbacks and other millisecond pulsars suggest that many of these systems follow evolutionary tracks in which a normal star fills its Roche lobe, transfers mass and angular momentum to this neutron star, and then once accretion slows is eroded by the pulsar wind. Along these tracks, some systems halt with a relatively massive white dwarf companion, while others, like this neutron star, continue to strip the companion down to a very low mass. The outcome depends on the initial mass's orbital separation and efficiency of angular momentum loss. The presence of this pulsar near the upper end of the neutron star mass distribution indicates that at least some evolutionary channels can build very heavy neutron stars without triggering collapse, while the small number of such extreme objects detected so far suggests that not all paths produce such high masses. Observationally, Black Widow systems like this one are challenging targets. Their companions are faint and often strongly variable with light curves, shaped by heating eclipses and sometimes surface inhomogeneities. The radio pulses from this pulsar can be eclipsed or scattered by plasma, flowing away from the companion, making timing more difficult at some orbital phases. Gamma-ray observations, while not affected by such scattering, provide fewer photons and thus require long integrations to build up clear signals. Extracting precise masses, spin parameters, and orbital characteristics from such data demands careful modeling and coordinated campaigns with multiple telescopes. Nonetheless, these efforts pay off in the case of this neutron star, yielding constraints on its mass and spin that feed directly into dense matter physics. As instruments improve, more Black Widows may be discovered, and some may host neutron stars with masses comparable to, or even higher than that of this pulsar. Each new measurement would refine the emerging picture of how common very massive neutron stars are, and how close this neutron star lies to the true maximum mass. Future radio arrays with greater sensitivity, wide-field gamma-ray observatories and optical facilities capable of precise time-resolved photometry for faint targets are expected to contribute to this work. Another way in which this neutron star connects to broader astrophysics is through its role as a probe of the interstellar medium. The radio pulses from this pulsar travel through the ionized gas that fills the Milky Way, and along the way they are dispersed. The amount of dispersion measured by the delay of a low-frequency pulses relative to high-frequency ones reflects the integrated electron density along the line of sight. For this neutron star, combining the dispersion measure with its estimated distance yields information about the distribution of electrons in the region of the galaxy it inhabits. This information feeds into models of the galactic electron density, which in turn are used to estimate distances to other pulsars and to interpret timing data across the pulsar population. Scattering effects which broaden the pulses in time similarly trace small-scale irregularities in the interstellar medium. The presence of a binary wind and evaporating companion adds further complexity, because material local to this pulsar also contributes to dispersion and scattering near some orbital phases. Timing observations that track these changes provide a way to separate interstellar and local plasma contributions, refining models for both. In this sense, this neutron star participates in two kinds of mapping, at once tracing the conditions in its own immediate binary environment and sampling the larger scale structure of the Milky Way. The binary geometry of this system also allows tests of gravity on scales larger than the star itself. Although the companion is too light to produce strong relativistic effects, like those seen in double neutron star binaries, precise timing over long periods can still reveal or constrain phenomena such as orbital period changes driven by gravitational wave emission, mass loss from the companion or variations in gravitational potential due to additional bodies. Any secular change in the orbital period must be consistent with the measured mass loss, and with the predictions of general relativity for energy carried away by gravitational waves from a compact binary with these masses and separation. While the current limits from this system do not rival the classic tests obtained from double pulsars, they add to the ensemble of binary pulsar experiments that collectively probe gravity in regimes of strong field but relatively slow motion. As more data accumulate, it may become possible to detect subtle trends in the orbital evolution of this system that inform models of how Black Widow binaries lose angular momentum and mass over time, In the broader astrophysical context, this neutron star therefore occupies several interconnected roles. A test of dense matter at very high density, a tracer of binary evolution, leading to extreme mass ratios and evaporating companions, a probe of the interstellar and local plasma environment, and a participant in precision timing experiments that touch on gravity and plasma physics. Its combination of mass spin and binary configuration makes it a focal point for these studies, and as observational capabilities expand, this pulsar is likely to remain an important reference object, linking the microphysics of nuclear interactions in its core to the behavior of the binary and to the structure of the galaxy that contains it. Within the inner regions of this neutron star, where matter is compressed to several times ordinary nuclear density, and where superfluid and possibly more exotic phases may exist, the focus of current research is on turning the broad constraints provided by its high mass and rapid spin into more detailed statements about the behavior of dense matter, and this ongoing effort connects observations, modeling, and laboratory work in a continuous loop. Observers continue to refine the fundamental parameters of this pulsar, seeking more precise measurements of its mass, spin-down rate, and binary geometry, because even small changes in these values shift the region of pressure and density space that must be occupied by its interior. In optical bands, campaigns that monitor the companion over many orbits work to improve the characterization of its atmosphere, surface temperature distribution, and response to irradiation, using refined stellar atmosphere models and time-dependent radiative transfer to interpret the observed light curves. These improved models aim to reduce systematic uncertainties in the inclination and companion mass, which feed directly into the mass estimate for this neutron star. In radio timing, advances in receiver sensitivity and data analysis allow pulses from this pulsar to be tracked with increasing precision, revealing tiny variations in arrival time that map not only the orbital motion, but also any long-term trends in spin-down and possible small irregularities. Over spans of many years, these timing data provide a more secure measurement of how rapidly this pulsar loses rotational energy, and when combined with models of its magnetosphere, they supply additional constraints on its moment of inertia, which is sensitive to the equation of state in the inner core. High-energy observations in gamma-ray and X-ray bands continue to build up statistics on the pulsed emission, and on any steady or variable emission from the shock, where the pulsar wind meets the outflow from the companion. By examining how the high-energy light curve changes with orbital phase, and energy researchers probe the geometry of the emission regions and the distribution of particles in the wind and shock. While these data primarily inform the exterior environment, they also feed back into estimates of the total power that this neutron star must supply through its spin-down, which again links to the interior through the moment of inertia. On the theoretical side, each incremental improvement in observational constraints prompts updated calculations of neutron star structure. Using families of equations of state that incorporate nucleons, leptons, possible hyperons, and quark matter in various combinations, theorists compute sequences of models that span a range of masses and spin rates, identifying those that can reproduce a star with the mass and spin of this pulsar while remaining stable. They then compare the predicted radii moments of inertia and tidal deformabilities of these models with constraints from other neutron stars and from gravitational wave observations of mergers seeking an equation of state consistent with all data. In this process, this neutron star serves as a boundary condition at high mass and high spin, while other objects supply points at lower mass or in different environments. Laboratory experiments on nuclear matter continue in parallel using heavy ion collisions and precision studies of nuclei to measure properties such as the symmetry energy and its density dependence. These measurements fix aspects of the equation of state near and below nuclear density, anchoring the low-density end of the relation between pressure and density. Extrapolations that extend these relations to the higher densities present in the core of this neutron star must remain compatible with both laboratory results and astrophysical constraints. As a result, the interior of this pulsar becomes part of a larger network of cross-checks between very different experiments and observations. Future facilities may add further threads to this network. Next-generation X-ray observatories designed for precision timing and spectroscopy could, if they detect thermal emission from hot regions on the surface of this neutron star, apply detailed pulse profile modeling that includes gravitational light bending and atmospheric effects to infer its radius. If successful, such measurements would provide the second coordinate needed to place this pulsar at a specific point in the mass-radius plane, sharply reducing the set of allowed equations of state. Likewise, more sensitive gravitational wave detectors might in time reach the threshold required to search for continuous waves from small deformations in rapidly rotating neutron stars. A detection, or even a tighter upper limit for this pulsar, would further constrain how much strain its crust and core can sustain, and how strong any unstable oscillation modes can be, which would again reflect the stiffness and composition of the dense matter inside. Even without these future measurements, the role of this neutron star in dense matter studies is already clear. Its high mass inferred from the dynamics of its black widow binary excludes soft equations of state that cannot support such a heavy object. Its rapid, stable spin shows that it can rotate hundreds of times each second without reaching the mass-shedding limit, which favors configurations that are not excessively compact for their mass. Its long-lived state after an accretion phase demonstrates that neutron stars can survive substantial mass gain without collapsing, provided that the internal pressure rises quickly enough with density. Each of these facts is encoded in the structure of this pulsar from the solid crust through the superfluid inner layers to the deepest core, and together they narrow the range of possible behaviors for matter at the highest densities. As observations and theory progress, this neutron star remains a central example, its properties serving as a reference against which new equations of state are tested. New models of neutron star evolution are judged, and new interpretations of gravitational wave and electromagnetic data are compared. The inner region explored here, where dense matter supports this neutron star against its own gravity, thus remains both an endpoint of the spatial journey inward and a continuing starting point for efforts to understand how matter behaves under the most extreme compression known in the Milky Way.